Good afternoon. We will wait 2 minutes more before we start. Okay, so it's 1:15, so we will start the lecture. Can you please confirm that you can hear me and that you see the slides? Okay, thank you. Okay, so yeah, my name is Grzegorz Soboń, and it will be my pleasure to have this lecture with you. So we will start with some formal introduction. There should be approximately 27 students in this group. We see 15 participants now, so maybe some people will join later, or if not, then that's not my problem. I'm available at room 204 in the building C5 at the campus. So if you want to contact me, reach me, then you are always welcome at my office. You can also call me. This is my phone number, office phone number. I have also assigned some office hours on Wednesdays between 1 and 3 p.m. I don't know your schedule of your other courses, but if it doesn't fit you, then you can choose any other date. So you can write me an email and we can just meet whenever you want. So I am available. I read emails and I respond to emails quite quickly. So if you need any kind of consultation or something, then just let me know, and by any means you choose, so Zoom, Teams, phone, or just email, or anything, right? Okay, so about the this course and the rules. So as you know, you have not only lecture from this this course, but also the laboratory and the seminar. So the laboratory will be probably with Dr. Paweł Kaczmarek, and the seminar with Professor Abramski. So to pass this course, you need to pass the lecture, the laboratory, and the seminar, right? And the final grade from the course will be kind of a weighted average, so 0.4. The lecture and the laboratory and the seminar have the factor of 0.3. So to pass the lecture, so passing the laboratory and the seminar, you will know the rules from your from other professors. And so about the lecture, there will be an exam after the semester because this course should end with an exam. So there will be an exam at the end. However, there are 2 midterm tests during the semester. So if you pass these both tests, so by pass I mean you need to have more than 50% of points from each test during the semester, then you don't have to write the exam. So you just get your grade and you don't have to go to the exam. But if you fail at least one of the tests, you need to go to the exam, and the exam covers the entire program of this lecture. So the first test will be on should be on 13th of April after 6 lectures. So 13th of April, this is Wednesday, but there is a change in the calendar so that Wednesday is changed to Thursday. So the first test would be here on 13th. So we have 6 lectures and then the test. The second test will be either on the 2nd or 9th of June. So this will be announced later by Dr. Kaczmarek, since in this in this lecture we split it into, let's say, 2 parts. So I will be responsible for the first 6 lectures and the test, and then the lecture will be handed over by Dr. Kaczmarek, and he will tell you about fibers. So I will have the laser part. So the first 6 lectures will be about lasers, and I will do this, and then you will have the part about fibers, and this will be Dr. Paweł Kaczmarek. And the final exam for those who don't pass the will not pass the midterm tests will be during the exam session, so after 23rd of June. So the main goal of this course is, of course, to gain knowledge about the basics of lasers. I would be really happy if you could, after these lectures, you could explain to someone how a laser works and know the fundamentals of lasers and the principles of operation. You should also know the main types of lasers, how these lasers are built, and how they work. You should know the main applications of lasers and just understand why lasers are so important for us, because lasers have numerous applications. That's why we need to learn about lasers. And during the laboratory, you will have the opportunity to gain some hands-on experience with lasers, mostly gas lasers, but also semiconductor lasers, fiber lasers, and just measure and verify their parameters. Just a small additional information for those who, due to some health conditions or disability or other reasons, have some special needs regarding to listening to classes, crediting, and so on. Please write me an email or just join the consultations to discuss with me this issue. So if you have any issues in this topic, then please contact me. So the plan of this entire lecture, of the first part that will be done by me, we start with a very basic introduction about lasers and some basic definitions. Maybe we will start a little bit about the physics of lasers. And then the second lecture will be about some information about amplification, quantum application, elementary transitions, some basic physics of lasers. Then we move on to laser resonators, especially the Fabry-Perot resonator, properties of these resonators. Then we move on to description of different types of lasers. So gas lasers, semiconductor lasers, solid state lasers, and then we will have to test. And then after the 7th lecture, so 6th lecture and the test, Dr. Paweł Kaczmarek will continue with this lecture on fibers and fiber optics. And one important remark, according to some internal rules, only 2 first lectures will be online. So we move to on-site from 17th of March. So the lecture on 17th of March will be in room 409 in the building C5. So only this one and the next one lecture will be done online, and I will send you the Zoom link. Regarding the literature, this is the list, so you can take a screenshot. There are, of course, many books on lasers, textbooks, and so on. So these are the ones that I recommend. I recommend maybe mostly the book of Orazio Svelto, Principles of Lasers. If you need any other literature, so if some of the topics will be particularly interesting for you and you want to have some deeper insight and you need some more literature, please contact me and I can recommend you something or send you some publications. Do you have any questions regarding the formal part? Everything was clear? Yeah, I don't hear any questions, so please mark the date of 13th of April in your calendars, because this will be the first midterm test. And you will write this test not online but on site here at the university. Okay, so we will start with the topic of today's lecture. So yeah, laser. What does this word actually mean? So laser is an acronym standing for light amplification by stimulated emission of radiation. And actually this acronym, as you can see, it already explains everything about lasers. So we have emission of light by the process of so-called stimulated emission. So I will explain you what the stimulated emission is. Yeah, maybe today if we have enough time, but most likely next week. So generally a laser is basically a device that generates light. And light is, of course, an electromagnetic wave. We can consider light as waves, but also as particles, as photons. However, during this course, we will rather consider light as waves, as electromagnetic waves. We will not go into, let's say, quantum properties of photons and so on, because this is totally outside the scope of this lecture. But of course, there will be some situations where we will need to refer to photons. Yeah, so this is a simple example of a laser that everyone knows. So just a laser pointer, like the one I have in my hand. So usually they are emitting green or red light, sometimes blue. So this is a laser. So the basic fact is that the laser generates the electromagnetic wave from the frequency range defined as the optical bandwidth, right? So this is something that we call light. So the most important parameters of laser radiation that we will also explore during the lecture are, first of all, the wavelength. So Someone might say color, but this is, let's say, unprofessional. Technically, we say wavelength or frequency, because wavelength is directly connected with the frequency of the wave. So we can use both units. So lasers basically generate light from the spectral range, ranging from the UV until the mid or even far infrared. The other parameter is the bandwidth of the emission, because lasers usually generate a monochromatic wave, but sometimes lasers generate also many lines, or the lines are broadened. So we also need to define the bandwidth of the emission. So the bandwidth is usually expressed not in wavelengths, but in the frequency domain. So it might span from hertz or even sub-hertz to gigahertz or even terahertz. We define the power. So some lasers generate very low powers at levels of nanowatts, microwatts, milliwatts. But there exist high power lasers that can generate even up to terawatts or petawatts. So petawatt it's a lot of power. We distinguish two types of lasers: pulsed lasers or CW, which means continuous wave lasers. So continuous wave is obviously a laser that continuously emits the wave, and the pulsed laser, obviously, it's a laser that generates pulses that are separated by some time period. So in case of a pulsed laser, we can define the pulse duration, and very often lasers can generate very short pulses, ranging from femtoseconds or even attoseconds. So femtosecond is 10 to the minus 15th of a second. So this is a really short pulse, up to milliseconds, microseconds, and so on. We also define the geometrical properties of the beam. So if you see the laser beam, you can define, you can say what is the shape, what is the beam quality, what is the beam profile. So this is the intensity profile of the cross section of the beam, and also the polarization. So polarization should be a definition that you should already know from electromagnetic field theory, but I will say a few words about the polarization today as well. So as a very brief introduction to lasers, one need to know that lasers can be really small devices. So this is an example of a small laser. So this, what you see here, this is a laser in a housing. But if you take out only this small can here, this is the so-called TO package, typical package used in packaging of semiconductor lasers. So this is here. If you look at the internal structure, you have the window, the output window, and the structure of the laser. The laser chip is here. So this is the real image. So we have the laser chip somewhere here. So it's really small, right, compared to the size of the housing. So these kind of lasers can be manufactured in millions of pieces of chips in some technological processes, like typical semiconductor manufacturing technology. So these are so-called VCSEL lasers, so vertical cavity surface emitting laser. We will also describe this type of laser during the maybe fifth lecture. On the other hand, lasers can be really big. So this is an example of a very big laser. This is the laser at the National Ignition Facility in the United States. So as you know, United States, this is a really big country, so they have a lot of space, so they can build big lasers. So this is an example of a big laser. There are people here for scale. So this is these are 3 people that are working in this laser. So this whole room, this is a laser. And this entire room is located here on the map of the entire National Ignition Facility, while the whole laser is here, right? So this is just one small part of the entire laser. So this laser is used for so-called nuclear fusion with lasers in the United States. So I'm wondering if you maybe can guess where is the most powerful laser in the world? Do you have any guess? The sun. No, the sun is definitely not a laser. So if someone tells me the correct answer now, we'll gain 1 point on the test. Okay, time is out. No answer. So the most powerful laser is located in the institute, which is called ELI, standing for Extreme Light Infrastructure, and it is located in Romania. They have a 10 petawatt laser. So petawatt is 10 to 15, right? Watt. So you should know that the power of milliwatts, which is 10 to minus 3, is already can already permanently destroy your vision of your eyes. And if you have like 10 to maybe this second, so some watts, you can already burn some holes in materials, or you can burn your hands and so on. So 10 to 15 is just an enormously high power laser, and this laser is located in Europe. So the very philosophical question is, why are lasers so important? So when people invented the laser in the 60s of the 19th century, they already knew that there are many important applications of lasers, and the laser will change the world. Nowadays, you know that people often use lasers for really silly applications, but this is not the only application of lasers. We will discuss the applications of lasers during the semester, but just a list to give you some impression about how impressive the number of laser applications is, because we can use lasers in many areas of our life. So like in medicine, in the military, in science, like quantum computing, optical data storage, quantum communications, gravitational wave detection, nuclear fusion, but also in like scanners or printers or CD players. So in these all applications, we use lasers, and all these lasers have the same principle of operation. There are of course different types of lasers, but the physics behind is the same. So when you accomplish this course and you will know how a laser works, you will know how all these applications are done. So lasers are also important because of the economic reasons. So here you can see some data, some financial data. What are the typical laser revenues on the market? So you see 14 billions of dollars, and also you can see what is the market share of specific applications. So the biggest part of the market are lasers for materials processing. So all the applications related to the use of lasers for processing of different materials like cutting, welding, splicing, drilling, marking, and so on. So a lot of components, like in automotive industry or in industry in general, are made using lasers. So laser machines that are used for cutting, precise cutting, or drilling holes. The next area is optical communications. So the entire fiber optic communications, high-speed internet. So if you have gigabit internet at home, you probably have an optical fiber at home, right? So for having broadband internet, you need to have a fiber connection. So on the other end of the fiber that you have at home, there is a laser on the other side. So if there are billions of customers that have internet from the fiber, you need to have billions of lasers. The next areas, R&D and military. So you probably know about laser weapons and all the applications of lasers in research. Sensors, instruments, so a lot of scientific instruments and laser sensors, like sensors of vibrations, velocity meters, dimensional ranging and measurement tools based on lasers. Medical applications, maybe someone of you already had some medical procedure done with lasers, like laser scalpels or tattoo removal. Lithography, so this is the connected with manufacturing of semiconductor chips, like microprocessors, transistors using lasers. Displays, laser displays, and some smaller areas like optical data storage and also printers. So this is the laser market. So we see lasers provide a quite huge revenue on the global scale. So there is a really huge market of lasers in the world. So it's also worth to mention about people who are responsible for lasers. So as you probably know, usually some inventions have a lot of people that were involved in this development, and the same applies to lasers. So these four gentlemen here, visible on this slide, they received Nobel Prizes for the development of the theory of optical amplifiers and generation of optical frequencies. So Russian scientists Prokhorov and Basov, and American scientists Charles Townes and Arthur Schawlow. So you see all of them received the Nobel Prizes, Prokhorov, Basov, and Townes in 1964. But since the rule of Nobel Prize is that only 3 people can at once have the Nobel Prize for the same achievement, Schawlow received the Nobel Prize a couple of years later. But these guys here, they invented the theory. They never built a working laser. They developed the theory and the general concept, and then just, let's say, out of nowhere, a physicist and electrical engineer, Theodor Neumann, who was working at a company at the time, he was not even working at the university. In 1960, he built and showed to the world the first working laser. This was a laser based on a ruby crystal. So he even holds here in his hand the parts of the laser. So this is just a flash lamp used for pumping, so delivering energy to the laser. And inside there is a ruby rod, which is responsible for emission of light. And this is the cavity, the housing. So Theodor Neumann is the guy who actually built the first laser. but he never received the Nobel Prize. There is also another person that we should credit. So Gordon Gould was the inventor of the acronym laser, and he also had some patents. He held some patents for different types of lasers, so he earned a lot of money. However, he didn't invent the laser. We should also mention the another Russian scientist, Valentin Fabrikant, who described the principles of optical amplification in 1951. So even before Shawlow, Townes, Basov, and Prokhorov, he proposed the amplifier of optical frequencies. So the later works of Shawlow and Townes were based also on the works of Fabrikant. However, still we need to go back a couple of years and mention Albert Einstein, who is well known for the, of course, some theory of relativity, but in general, he received the Nobel Prize for the quantum theory of radiation. So his theory gave the possibility to invent lasers. So for that, he also got the Nobel Prize. So we would say he's the, let's say, grandfather of lasers. If you're interested in the history of lasers, I can recommend you a book written by Theodor Neumann, the inventor of the first laser. There is also a Polish translation, Odyseja Laserowa, available, or just the Laser Odyssey in English. So I encourage to take a look if you are interested in the history of laser and the route path that Neumann was following to finally build and show the first working laser. So it's a really nice book. So I encourage you to read. It is also worth to say that working with lasers increases the probability of getting a Nobel Prize, because if you look at the this set of people, these are all Nobel laureates who were members of the American Optical Society. So all of them worked with lasers or with optics. Of course, maybe the first guys didn't work with lasers because lasers were invented here in 1960. So you can see that there are a lot of Nobel laureates somehow connected with lasers. So it's a good topic if you want to be a Nobel laureate. And the very recent Nobel Prize in 2018 was also awarded to people working with lasers. So Arthur Ashkin, Gerard Moreau, and Donna Strickland. Arthur Ashkin for development of so-called optical tweezers for trapping of particles with laser light, and Gerard Moreau and Donna Strickland are the inventors of the so-called CPA technique. This is chirped pulse amplification. This is a technique of amplification of laser pulses to enormously high powers. So the National Ignition Facility that I showed you, or the Eli Institute, the most powerful laser, is based on this concept. So it wouldn't be possible to build all these huge laser infrastructures without the invention of Gerard Moreau and Donna Strickland. And they, as far as I remember, they invented this in around 1986 or something like that. And they got the Nobel Prizes in 2018. Okay, so that's about the history of lasers, just as a very brief introduction, just to give you an impression about how old this device is, because lasers have already 60 years, but they are still being developed. We still don't know everything about lasers, and we still build new lasers, develop lasers, and the market is still growing. And we still see new applications of lasers, because you saw that the market is still growing. So economically, lasers are on the rising edge. So despite the 60-year-old history. Okay, so today we will continue with some basic definitions that are important, because we need to we will use them in the future. So generally, as you know, we consider the optical band as the bandwidth in the electromagnetic spectrum between the ultraviolet, the UV, and the infrared, right, range. So this is the optical band, but generally the optical waves, so light, the same type of electromagnetic radiation like radio waves, but just with a slightly different frequency. And please note that the visible radiation is just a very tiny slice of the of this entire electromagnetic spectrum. So the light that we can perceive as visible, right? So this is a really small range that spans over approximately 300 nanometers, maybe up to almost 400 nanometers. So this is a really very narrow slice of the optical radiation. And I am not even using any visible laser in my daily work with lasers. So as we agreed, lasers emit electromagnetic waves, and electromagnetic waves propagate and behave according to some rules like defined by the Maxwell's equations. So I assume that you're familiar with Maxwell's equations, so I won't describe that, but it's just to remind you that we are still talking about electromagnetic waves, so all these equations apply. What is important is that the Maxwell equations, they lead to the so-called wave equation. So we can derive the wave equation from the Maxwell's equations. And the wave equation is here. And it is important for us because one of the solutions of the wave equation is the plane wave. So this is the wave that we will we will consider light as just as a plane wave, right? Plane wave means plane because this wave front in this wave is flat, right? So we consider that this is just a plane wave front that is propagating in the direction, let's say z, right? So let's say this can be the z-axis. So this is just an illustration of how the plane wave is propagating. So the plane wave has, of course, an amplitude and some direction and some frequency and also phase of the wave. And the plane wave is also called a transverse electromagnetic wave, so a TEM wave. TEM because the vectors of the electric field and the magnetic field are perpendicular to the propagation of direction. So if this is the propagation of direction here, so these two vectors are perpendicular to each other. So that's why we call the plane wave a TEM wave. So we will also consider light as this type of wave. So let's take a look at some spectral properties of these waves. So if we assume a plane wave that propagates in direction z, right, in time. So let's ask a question: what is the spectrum of this wave? So if you want to calculate or predict the spectrum, what do we need to do? We need to make a Fourier transform, right, out of it. So if we make a Fourier transform of this kind of function, which is just a cosinusoidal function, as a result, we get the Dirac function, right? So you are, so you're familiar with the Dirac function, which is infinitely narrow. So it means that in the spectral domain, the spectrum of a plane wave, of a monochromatic plane wave, should be just a Dirac function. So an infinitely narrow spike in the frequency domain. And this is, of course, true, but in real life, we don't have ideally monochromatic waves, right? Because lasers, as you might know, lasers can generate nearly monochromatic waves, but they are not monochromatic in the ideal sense, right? They they might be very narrow in the frequency domain, but they are really close to ideal sine waves, but not ideal, right? Because we have some, of course, some kind of noise and some fluctuations of the phase in the wave. So this will translate into if you make a Fourier transform out of it, we will see that we observe some spectral broadening. We have also the effects of line broadening in lasers, but mostly affected, the line shape is affected by some fluctuations because of environmental factors. That's why the laser line gets broader. So that's why we cannot have an ideally monochromatic wave. But if we could isolate the laser from any disturbances, the ideal situation theoretical would be a monochromatic wave, which would be just a infinitely narrow Dirac delta function. So if we speak about line width of light, of laser light, we need to introduce the definition of coherence. So coherence is basically the ability of the wave to interfere, and especially to interfere with itself. So interference, as you know from electronics and also from acoustics or from radio waves, this is just, say, overlapping of two or more waves and creating a third wave, another one, right? So if we consider two waves here, and they are in phase, so you see that we have the same phases, and we somehow join them together, so we overlap them in space and in time. They will interfere together and they will create the interference pattern, the interferer beam wave, which will have the intensity proportional to the sum of the both waves. So they will just sum up. But if we shift the phase of one of the waves, so they will be out of phase, as you can see here. If we add them together, their intensities will cancel. So we will have just zero field after the interference of that, right? So this is interference. And there is an effect of coherence that is connected with the definition of interference. So to explain what coherence means, we will use an example of a Michelson interferometer. So Michelson, the Albert Michelson was also a physicist who was awarded with the Nobel Prize. Interestingly, he was born in Poland, in Strzelno. But when he was a child, he moved to the US. And then he worked on light waves, and he was awarded with the Nobel Prize. So we will start with the Michelson interferometer. So the Michelson interferometer is a very simple optical setup that consists of a beam splitter. So this is just a plate that splits the beam into two parts, and then we have a mirror here. So the first mirror that is fixed, and we have the second mirror that can be moved. So when the incoming beam is divided into two parts using this mirror, one part will be reflected here, and it will be reflected by the mirror and will go back to the beam splitter. The second part will propagate here, be reflected from the mirror, go back to the plate, and both beams will interfere in this beam splitter, and we will observe this interference here using a photo detector. So you can guess that if we make this interferometer in the way that the distance L1 here and L2 are equal, so L1 is equal to L2, we will have the situation which is plotted here, right? So because both waves, they need to travel the same distance, so they will have the same phase, so they will interfere constructively, right? So we will observe here the sum of these two waves. On the other hand, if we move the mirror by a very tiny step, so that we shift the phases shift the phase of one of the beams, so that they will be totally out of phase. So we need to shift it by half of the lambda. We will obtain destructive interference, so we will not see any intensity here, right? So this interference equation, so this interference process is described by this really simple interference equation, but this is not so relevant, so I don't force you to remember that, but the result is important. So the resulting interference, intensity of the interference equals E1 plus E2. So these are the intensities of the two incoming beams. And then we have a root of the product of the intensities, and we also have the phase relationship here, right? So the phase shift is important, because when we shift the phase so that the beams are out of phase, we will not have the interference. So for an ideal, let's consider now an ideally monochromatic wave. And let's assume that we have these two arms equal. So we have the mirror here. So L1 is equal to L2. So we have constructive interference, because we have both beams in phase. If I move the mirror back, so I change the phase of this beam here, I will see that the intensity of the output beam that I measured here in this point will drop because one of the beams starts to be out of phase. So the resulting interference will be weaker. And finally, I get to the point where my waves are shifted by half of the lambda. So then I will have 0 intensity. But then I move even further my mirror. So then I again move to the point where I have a maximum, right? And so on and so on. So I can move this mirror, and I will periodically see that the beams were in phase, out of phase, in phase, out of phase, and so on. So this is seen here on this animation, right? And the question is, can I move this infinitely far away and see this interference pattern? And the answer is unfortunately no, because this is related to the so-called coherence length of laser light. It turns out that in real life, after some distance, we will observe that our interference gets weaker. So we will see a loss in this modulation depth of this interference signal, right? So we will see that when we move one of the mirrors far enough, we will observe that there is a loss in this interference modulation. So the beams don't want to interfere anymore. So we define a parameter which is called length of coherence, which is twice the delta L. So this separation between the this difference between the lengths of the two arms, right? Twice because the beam needs to go in one direction and to the back. So the length of the coherence is the length 2 times delta L, for which the interference pattern disappears, because at some distance the interference pattern will disappear. My question is, do you need a break? Because I didn't ask for that before. We can continue without, or I can make a break. This is up to you. Do you have any preference?
We can continue.
Okay, if no one disagrees, then I will continue. So the coherence length is connected, is connected with the time of coherence, but this is maybe not relevant. But the coherence length is defined as the velocity of light divided by the spectral bandwidth of the laser source. So this is why I was talking about spectral bandwidth of lasers, because this will affect the coherence. So if, as you can see, if the source would be infinitely narrow, we would have, of course, infinitely long coherence length. But in real life, we have limited, let's say, limited bandwidth. So that's why the coherence length will not be, of course, infinite. So as you can already see, the broader the bandwidth of the source, the smaller the coherence length. So if I have a broadband light source, I will have really quickly I will see really quickly that my interference pattern disappears. And this is important because for practical reasons, because this means that lasers with broad bandwidth are not suitable for interferometry and for all applications where we need to see interference. And I have it on some next slide. Yeah, here. So here you can see some examples of coherence length of selected light sources. So for example, an LED, so just a light emitting diode at the wavelength, let's say, of 600 nanometers, so just a red diode. It has a bandwidth of some tens of nanometers, right? Let's assume 30 nanometers. So if you calculate the coherence length, this will be 0.1 millimeter. So this is a really small coherence length. So we will not be able to use LED as a source for interferometry. On the other hand, if we look at the let's say other types of semiconductor lasers, like semiconductor diode laser or telecom diode laser, you see that the lines start to be much narrower. So the coherence length starts to be quite large. So for a telecom diode, we have 300 meters. But if you consider, for example, a very stable gas laser, which has a very narrow line width at the level of, let's say, even 1 hertz, then the coherence length reaches 300,000 of kilometers. So you can measure pretty nice distances, which is important for some particular applications. So in general, we can say that a high quality laser would be a laser that will have a very narrow line width and will be close to monochromatic, because then it will have a good coherence and it will be a good tool for metrology. On the other hand, the LEDs or broadband diode lasers, they have low coherence and they will not be suitable for metrology. And what is important here, and I want to emphasize that this is very important, is that we can, in optics, we can express the bandwidth, the spectral bandwidth of the source of the laser, either in the wavelength domain or in the frequency domain. Okay, so because this is basically the same, right? Because we can express, so this is the frequency, so this letter null, this is frequency. So if you want to switch between frequency and wavelengths, you just need to take the speed of velocity of light and divide by the wavelength, and you have the frequency, right? So we can switch between these two units, right? But if you want to calculate the bandwidth in the frequency domain or in the wavelength domain, then you need to differentiate this equation, and you get this here. So if you know the bandwidth in the wavelength domain, so for example, I know that my laser has the wavelength lambda of let's say 1550 nanometers, and the bandwidth, so the delta lambda equals 1 nanometer, then I can do the math and calculate the bandwidth in the frequency domain. So we can switch between these two units, and this is important. So please remember this equation, because you should be able to switch between the units in different lasers. So why we do this? Why we make it so hard that we use two types of units? So the answer is simple. Sometimes if the laser line is really narrow, so we measure the width of the line in the so-called full width at half maximum. So we measure it in the half of the maximum, right? So we measure it here. So this is the 50% of intensity. So if the line is very narrow, we usually express it in the frequency domain. So in megahertz, in hertz, kilohertz, and so on. But if it's broad, then we rather express it in nanometers in the wavelength domain. This is because, let's say that we have a laser that has the wavelength of 632.8 nanometers, and the bandwidth of 1 hertz. So 1 hertz in the optical domain will correspond to a very, very small number expressed in picometers. So this is a very unusual unit that is rarely used. So it's easier to express it in hertz rather than in meters, right? But this is basically the same, so you can easily switch between these units. So I recommend you to try at home to do some recalculations. So for example, a laser emitting a wave of 1550 nanometers corresponds to the frequency. This is the frequency of 193 terahertz, and the bandwidth of 1 nanometer corresponds to the bandwidth of 125 gigahertz. So this is not a narrow line. We can say that a narrow line for a laser should be something that is less than kilohertz. So this is a narrow line, right? Or maybe less than some hundreds of kilohertz. But if it's more than megahertz, then we say that this is a broad laser line.
I'm sorry.
Yeah.
I have a question about this narrowness, this bandwidth. If we have a laser that isn't continuous, that has works in short pulses, if you have really short pulses, will it have higher bandwidth because the measurements uncertainty?
I saw your question in the chat. I want to answer later. Yeah, but in case of pulsed lasers, the situation is a little bit more complicated, but I can maybe I can quickly. Do you see the whiteboard?
Yes.
Yeah. So if you consider a short pulsed laser, so in time you have a short pulse, let's say femtosecond. If you want to generate a short pulse, you need to have a lot of bandwidth, right? Because something that is short in time requires a lot of bandwidth. So if you look at the bandwidth of a short pulsed laser, so let's say in the wavelength domain, say this is the power, this is the power. So the bandwidth will be really broad, like tens or hundreds of nanometers, right? So this will be a really broad bandwidth. So the first impression would be that this is a really broad bandwidth, so these pulses are not coherent. But this is not true, and I will tell about that on one of the lectures later, because this broad bandwidth that corresponds to these short pulses, in fact, consists of narrow lines, equidistant lines, so equally spaced, which are narrow, but they only have this envelope of this broad spectrum. But if we look at each individual line in the wavelength, or in the, let's say now maybe in the frequency domain, they are really narrow. So they might have like hertz or kilohertz line widths. So the coherence of a pulsed laser, of a very short pulsed laser, is really high, because we look at the coherence of individual lines, not at the coherence of the entire envelope, right? So I hope that this answers your question. Oh, sorry, I stopped.
Yes, thank you.
But I will explain it in more detail in some few weeks, because this will be related to the term of mode locking. But it doesn't translate into any uncertainty in the frequency measurement, because we are able to measure the frequencies of short pulsed lasers with uncertainty of 10 to the minus 18. Right, so this is a really stable source, and basically all the ultra stable lasers, the most stable lasers and frequency references, are based on pulsed lasers. So this short time doesn't matter because these pulses repeat in some time period. So you basically average over a large number of pulses, right, during your measurement. And 10 to the minus 18, this is a really precise measurement, because if you consider that you could measure the size of an object using just a ruler, then you have the fractional uncertainty at the level of, I don't know, maybe 10 to minus 3, 10 to minus 4. So here we have 10 to minus 18. So this is really precise measurement. But I will continue this topic maybe later. But that's a good question. Okay, so it's important to be able to switch between these units. So the general message is that high quality lasers are narrow line width, but not always, but general. So why do we care about this coherence? Yeah, because of some particular applications like interferometry. So for example, you might know this experiment, which is called LIGO. This is the Laser Interferometer Gravitational Wave Observatory in the United States. This is a quite large infrastructure. As I said, the United States, this is a huge country, so they have a lot of space. So they have two interferometers. One is placed here in Livingston, Louisiana, and the other one in Hanford, Washington. And the principle of this network of two interferometers is that if in some point of the universe, two black holes will collide with each other, let's say here, they will produce a gravitational wave. And this gravitational wave will propagate, and it will meet with our Earth. And these interferometers are built to detect these waves, right? So when this wave propagates, it will firstly be measured in one of the interferometers, and then after some time, it will be measured here in another interferometer, right? So by having two of them, we can distinguish from which direction the gravitational wave was coming. But yeah, still, what about coherence? In order to detect a gravitational wave, which you can guess this is not a huge disturbance of the matter and air and in the environment, they needed a huge interferometer. So there is a laser somewhere here, and the mirror is placed like 4 kilometers, I think 4, but maybe 2. I don't know, but 4 kilometers, I think. This is the optical path here. So they needed to have a really coherent source because they move the mirror like 4 kilometers far away from the source, right? So for that, they use a quite stable special type of laser, which is here in the laboratory on a very thick optical table, so isolated from all types of vibrations, acoustic vibrations, and so on. So this laser was used for this huge interferometer, and they were successful. So they observed this this gravitational wave. So the conclusion from that is that they couldn't use just a semiconductor laser or a LED or anything, or like sunlight, because of not enough coherence. So if you need to make some precise measurements, you need to have a narrow bandwidth, narrow line width source with well-defined frequency and a high coherence. Okay, so the next definition that we need to introduce is polarization. So I assume that you have heard about this term in in the context of radio waves or some satellite communications and so on. But this also works in optics, right? So let's assume that we have a electromagnetic wave and we consider only the electric field here, right? So this is a plane wave. So we can write it as a superposition of two orthogonal waves, Ex and Ey. So these are the two components, X and Y components of the electromagnetic waves. And we can introduce some phase shifts between them. Here you have these deltas. So these are the phase shifts of the X and Y components. And this can be seen here on this animation. So we have the E, in my equations, this was Ex, but it doesn't matter. So we have these two components, Ez and Ey, which are orthogonal, and they will propagate in the direction here t. So they will propagate in time in this direction. And as you can see at the beginning, these two waves, they have the same phase. So they are in phase. So if you see these vectors, they are oscillating in one direction. So the resultant wave, so the superposition of this, will be the green vector, right? So you see that this vector is oscillating on just one straight line. So it means that this this wave is linearly polarized because this is just a straight line. So the line that is drawn by this green arrow. But if now we shift the waves by a quarter cycle, so we delayed the red one, right? And we now look at the resulting vector. You see that this displacement causes some kind of circular movement of this resulting vector. So it means that this beam is circularly polarized. And in this case, you can see that this vector is circulating counterclockwise. So we say that this is a left-handed polarized light. But if you would shift the blue wave with respect to the red one, we would have the oscillation in another direction. So this would be the clockwise direction. So this would be the right circular polarized light. So depending on the phase shift that we apply to these waves, we can have linear polarization. This is the first case when the beams are shifted by pi, or the integer multiplier of pi. The second case is when we have pi over 2. So we have a circularly polarized waves. And if this is a positive shift or negative shift, we have the right polarized or left polarized light. And the third case, which is not m pi and not half pi, this would be an elliptical polarized light. So this is any case which is not circular and linear, will be elliptical, right? So this is the polarization. Polarization is important in lasers and in optics, because if we deal with polarized light, we can also achieve some other parameters of light. So it's easier to manipulate with polarized light. So the question is how to polarize light, basically. So it's quite easy. So we can use either a polarizer. So this is a device which is a medium that can polarize light. So like a wire grid polarizer. So a set of a grid of small wires, thin wires made of some kind of metal that can polarize the field. You can use birefringent media. So these are so-called displacers that can split the incoming light, which is unpolarized or consists of two orthogonal polarizations. This displacer will split the beams into two orthogonally polarized beams. So they will be physically separated, and also we will have different polarizations. Also, reflection polarizes light. So if we reflect the light from a surface at a certain angle, so this is an important angle here, the reflected ray will be polarized. And this is the principle of operation of, for example, polarizing glasses, because the light which is reflected from the wet road, for example, is polarized. So we can easily cut it out when we apply polarizers to the sunglasses, right? So you can cut out the polarized part of the light. The same applies to photography. So if you take pictures, you very often see this kind of situation where you have a lot of light in your photos, which is coming from polarized light, polarized from reflection from water. But if we place a polarizer on the camera, you can get rid of these reflections. Okay, so this part was about some basic definitions of that we will use in description of light and laser beams. And now I would like to talk for a couple of minutes, since we have some minutes left, about the, let's say, physics of lasers, and I can start the description of how the laser actually works. So we will start with the introduction of the Einstein's theory of radiation, which was proposed over 100 years ago, but this is really important to understand the principles of lasers. So basically, Einstein assumed that atoms can exist only in certain discrete energy state, and each state has its own quantized defined energy. So it means that we can assume here an atom which has two energy levels, just for simplicity. We assume that we have an atom of some element. This is our imagined element, and we have two energy states, the first one and the second one, right? And they have discrete values of energy, so E1 and E2. So the atom cannot be at a level like here. So the atom can have either energy E1 or energy E2. So let's assume that we have this system, and for example, let's assume that we have an atom which has energy of E2. So we somehow delivered energy to our atom, so it is on the second energy level, the upper level, right? Because it has some energy. So after some time, it might happen that this atom will lose its energy and decay to the lower energy level. And it might happen that the atom loses the energy by emission of a photon. So it might happen, but it might also not happen, because there exist radiationless transfers, but maybe they might be also a radiation transfer. So we will emit a photon, and the energy of the photon will be equal to the difference between the energy of state 2 and energy of the state 1. And this will be equal to the Planck constant times the frequency of the photon. So this is the principle. And the state 1, the lower energy state, is called the ground state. So in the equilibrium, in the thermal equilibrium, if we have a container of atoms and it's in the thermal equilibrium, most of the atoms will be in the ground state. And the population of the state is described by the Boltzmann distribution, which will be shown on the next slide. But if we want to move the atom to an upper energy, we need to deliver to the system the energy that is at least equal to delta E here. So if we would need to deliver the energy by light, by photons, we need to have at least this energy of the photons. So this is the Einstein's approach. To give you some impression about the typical values of this energy gap in typical wavelength ranges. So let's say for the green emission, which is 500 nanometers around, and the frequency of around 600 terahertz, the energy expressed in electronovolts equals to 2.5. So we need some electronovolts of energy, right, to overcome this band gap. So as I said, in the thermal equilibrium, the population of the ground state is described by the Boltzmann distribution, shown here. So the Boltzmann distribution is proportional, of course, to the temperature and the Boltzmann constant. So if we consider the population of the nth level, here it strongly depends on the temperature. So what does it mean? It means that if we increase the temperature of this container, so let's say we heat it up, we will increase the population of the upper energy level, because when we increase the temperature, we will deliver energy to the container. So we will cause that some of the atoms will receive this energy, will absorb this energy and move to the upper energy state, right? So this depends on the temperature. And if the temperature is equal to 0, there are no atoms in the upper energy level, but they occupy only the ground state. Of course in the absolute 0 temperature, which is not possible in real life, but you can be really close to that. So in room temperature, we will always have some populations of the upper energy level. So now let's consider if this temperature dependent population has any kind of influence on the population of the upper level. So this table shows you the population of the upper level, E2, at different temperatures in the thermal equilibrium. So if we consider atom with delta E corresponding to green emission, to green color, we see that we have a very low, still a very low probability of occupying the upper energy state, so 10 to minus 9, 10 to minus 5. But if we go shorter with the wavelength, so then we decrease the delta E, then it's easier to obtain some populations in the upper energy levels by just increasing the temperature. So it means that in case of lasers emitting visible radiation or near infrared radiation, the temperature doesn't matter so much for the populations of the energy levels, But if we go to the mid-infrared, it starts to be important because these energy levels are really close to each other. So it's possible to destroy this thermal equilibrium by just heating our container of atoms. Yeah, so continuing the Einstein's theory, Einstein proposed 3 elementary transitions that can occur in this kind of system. So if we still assume this 2-level system, right? So we have an atom that can have 2 energy levels, 1 and 2. So now let's assume that we have an atom in state 2. So this is the upper state. So after some time, as I said, the atom can decay to state 1 and it can lose the energy by emitting a photon. And the energy of the photon is equal to the Planck constant times the frequency of the photon. And the parameters of the photons, this photon which is emitted here, is completely random. So the phase, the direction, the polarization is random. So the photon can be emitted with the same probability in any other direction with any other phase and polarization. And this process is called spontaneous emission. So this is the first elementary transition, spontaneous emission. Of course, there is a probability of spontaneous emission. So the probability is described by this equation. So there is an Einstein's coefficient of spontaneous emission. And basically, if we consider a container, again, the container of atoms, if we have a thermal equilibrium and no other process takes place, after some time, we will observe that all the atoms will just emit the photons after some time, and we will occupy only the ground state. So the population of state 2 will just run downhill with the time constant, which is described here. So if we plot the population of N2, we will see that it just drops in time with this time constant because of this probability. Because this is proportional to time, right? dt is the time constant. So yeah, so this is spontaneous emission. So please remember that spontaneous emission is just the atom can randomly decay to the lower energy state and emit a photon, and the parameters of the photon are random. The second elementary transition is absorption. So this is also simple. So let's assume that we have this system and we have an atom in our in the ground state. So now we have the atom in ground state, but we have an incoming field. So we have some electromagnetic field that is coming from this direction. So this might be a laser beam, for example. So the atom, if the energy of this beam is equal or higher, but should be equal to this delta E, this atom will absorb this energy from this incoming field and jump into the second energy state. So it will just absorb energy and move to the upper state. And the probability of this transition is proportional to the intensity of the incoming field, is proportional to the time constant and also to the Einstein's coefficient of absorption, which is specific to some kind of certain kind of materials, right? But the longer we wait, then we increase the probability, and the higher power of the incoming beam, also the higher the probability of absorption. So this is the second transition. And the third one, the most important one, is called stimulated emission. And this is the less intuitive one. So in stimulated emission, we have our atom in state 2, so in the upper state. And we also have the incoming field. So when the energy of the incoming field equals delta E, this atom can will decay to the ground state due to this external radiation, because this external radiation stimulates a coherent photon from the atom. So at the output, we will have two photons with the same direction, the same polarization, and the same phase and the same frequency. So the incoming photon from the incoming field, so this photon here, causes emission of another photon from this atom that will decay to the ground state and emit an exact copy of the first photon. So they have exactly the same parameters. So in contrast to spontaneous emission, where the photon is random, in stimulated emission, the emitted photon has exactly the same parameters as the incoming photon. And again, we have the equation that describes the probability. So again, we have the coefficient, which is the Einstein's coefficient of stimulated emission, the intensity of the incoming radiation, and the time constant. And these three transitions lead to the presence of quantum amplification, which I will continue during the next lecture. Do you have any questions?
Yes, I have one question.
Yeah.
So during this first two type of emission, like their probabilities are almost equal, right?
Yeah, they are maybe different because the coefficients are different. Because you have B12 and B21, so they these coefficients, they not necessarily are equal, but in some cases in lasers they might be equal. That's true. Yeah, there was a question in the chat. Would you upload the slides to the portal? Yes, I will. Do you have any other questions?
So for the stimulated emission, when we provide this delta E energy, is it possible just accidentally of this atom on the further layer, upper layer, so for the third layer, or it is important for this to provide the delta E energy, which is between those levels 1 and 2, because for the 2 and 3 is different energy. So
yeah, it's possible. So I don't want to spoil because this will be on some next lectures, but normally in lasers you have 3 or even 4 energy levels. That depends on the design of the laser, and usually we want to move from the ground state to the upper level, right? Without touching this level. So we need to use more energy. So the delta E should be here in this case the energy of the third level minus the energy of the first level, right? So we need to have higher energy to reach higher energy levels. So in case of this kind of system, if we have more energy levels, you need to know the energy of the levels so that you precisely choose the energy of your incoming beam to match the energy of the states so that you can move the atoms to specific states, right?
Yes, so it's not possible for while giving the energy between level 1 and 2 to match the level 2 and 3 to increase this atom. So
yeah. No, it's not possible. But there is also another process which is called 2-photon absorption or 2-photon excitation. So if you have a 3-level system and you want to excite the second level, right? So you want to populate this level. So you deliver energy equal to this difference here, right? Between 2 and 1. But it might happen that the atom absorbs 2 photons. So then you excite this state, which is might be, let's say, unwanted or just spurious. So you sometimes don't want to have that. So it might happen that you have this situation. But if you want to, if you have the energy equal to delta E, you cannot excite normally like the level that would be here, for example, because you don't have enough energy.
yes, thank you.
Okay. Okay, so if there are no further questions, we meet in 1 week. I will send you the link, the Zoom link, just maybe 1-2 days before the lecture. And in the next 2 lectures, we meet here on site in the lecture room. Okay, so thank you.
Thank you. Goodbye.
Bye-bye.
Bye.
Thank you. Goodbye.